So in part 3 of section 3.2, we're going to kind of switch gears and go back to the equation of a function. So this is example 3 on the handout. It says we're going to let f of x equal 2x squared minus x minus 1. And part A is asking, is the point -1, 2 on the graph of that function? So if we were to graph that function, would this point be on the graph? So it's a yes or no kind of question. You just simply have to remember that this is the x value, this is the y value. So the x is our input, the y is our output. So we're basically being asked to find f of -1, and hopefully the answer is 2. So that would be 2 times -1 squared minus -1 minus 1. Well, a -1 squared is a positive 1. The double negative on that 1 is going to make that positive. So we end up with 2 plus 1 minus 1, which sure enough is 2. So yes, when we plugged in a -1, we got out a 2. So the answer to the question is yes, that point is on that graph. Part B is saying if x equals -2, what is f of x? Well, they're asking us to plug in -2. So f of -2, we can do that. So every place we have an x, we're going to plug in a -2. Watch your signs carefully. So -2 squared becomes a positive 4. Double negative again will make that a positive. So we're going to end up with 8 plus 2 minus 1. Well, that's 10 minus 1, which is 9. So the input is -2, the output is 9. And it asks us what point is on the graph. Well, that would be the point -2, 9. So we're definitely trying to make the connection between inputs and outputs and points on the graph. Part C kind of asks the opposite question. It says if f of x is equal to -1, what is x? So they're not giving me the input this time, they're giving me the output. So I'm going to replace the f of x entirely with -1. And now we have to go find x. 2x squared minus x plus 1. We need to solve for x. Beautiful. Okay, so to do this, because it's a quadratic, we're going to move everything to one side. So 0 is equal to 2x squared minus x. The ones are going to cancel. And then we have to factor. We can plot an x. That leaves me with 2x minus 1. So x equals 0. And then 2x minus 1 equals 0. So x would be a half. So we get two values. And that's okay. We can have two x values with the same output. Nothing wrong with that. What points are on the graph then? Well, one would be 0, -1. Input x, output -1. The other point would be 1/2, -1. Input 1/2, output -1. What about the x-intercepts? Can I find the x-intercepts of the function when I don't have the picture? Oh, sorry. The next part is D. The domain. I skipped the domain. So again, to find the domain, you ask yourself those three questions. Does it have a radical? No. Does it have x in the denominator? No. So then its domain is all real numbers, or -infinity to infinity. That was easy. Okay, part E is the intercepts. We want to find the x-intercepts. We'll find the x-intercepts we know from previous work in the last chapter that we set y to 0. So we're taking our function and we're going to set that function equal to 0. Now we need to solve that. So we'll factor it. So it factors into 2x plus 1 and x minus 1. So x is a -1/2 and x is equal to 1. So if we write them correctly as intercepts, one intercept is at -1/2, 0. The other intercept is at 1, 0. So right now we could graph it if we wanted to. We found 5 different points, right? More than that. We have the point from part A, the point from part B, 2 points in part C, and 2 points in part E. So we could graph this and get a really pretty picture out of it. But there's our x-intercepts. And then finally, it asks you for the y-intercepts. And for the y-intercepts, this is part F. Y-intercepts, we know that we let x equal 0. So that would be f of 0, which is going to give us -1. So the y-intercept is at 0. So again, to get the x-intercept, you set the function equal to 0. To get the y-intercepts, you replace x with 0. Okay, example 4, I'd like you to actually take a look at really quick before we go to do it. You're matching pictures to graphs. You see 4 pictures. actually 5 pictures. Get them all? Yeah. And then there are descriptions of them. So this is example 4. It simply asks us to match each of the following functions with the graph that best describes the situation. So I'm going to do process of elimination more than anything else. It works quite well. You'll notice that the X and Y axes are not labeled with words, but I think it would really help if we had them with words. So we have the cost of a building as a function of its square footage. So it makes sense to us that if the bigger the house, the more it costs. So we need it to be an increasing kind of function, and that's going to be this one. So this is the cost of the house as a function of its area, the square footage. So this would be A. Okay, the height of an egg dropped from a 300-foot building as a function of time. Well, the egg's going to hit the ground. So I need something where it's hitting the ground at the end of it, and that would be this guy, right? So if this is height and this is time, after a certain time, it's going to smack into the ground and break. So this would be B. The height of a human as a function of time. Well, you grow so tall and then you stay that height for the rest of your life. And so we need something that goes up and then stays constant. So this would be the height of a human as a function of time. So this would be C. Okay, we're getting there. The demand for Big Macs is a function of price. So if a Big Mac was $20, would you buy it? I would not. So by this one, we have to be this one because it's not going to go back and forth like this. It's just decreasing. So over here, we have the price. And this would be the demand. So this is part D. And by default, the height of a child on a swing, which makes sense. Your height's going up and down as time goes on. So this is time. This is your height again. And this would be. So now we match them up.